In this video, we present Unit 16, which focuses on the magnetic induction. In the previous unit, Unit 15, we saw that charges moving, like currents, were able to generate magnetic fields. In this unit, in Unit 16, we will see that magnetic fields that change in time can be able to induce currents. So we will start this unit by focusing on the magnetic flux, which is similar to the electric flux, but instead of using the electric field, we will use the magnetic field. Then we will proceed to present Faraday's law, which shows the electromotive force induced by the change of magnetic flux through a surface. And then last, we will just present Lenz's law regarding the sign of the induced electromotive force. So to begin with the magnetic flux, I want you to recall when we define the electric flux. When we define the electric flux, we were saying that the electric flux is a scalar quantity that shows how many electric field lines across a certain surface. Okay, so this is the same with the magnetic flux. So it's a scalar magnitude again that measures the number of magnetic field lines that cross a surface. So if we have an arbitrary surface like this one here, like the green one, we will just have to calculate we'll just have to integrate in each little piece of surface the scalar product between the magnetic field and the differential vector that contains the small area of that small part. So this was very similar to what we did in the electric field. So now instead of having the electric field, we will have the magnetic field. The units of this magnetic flux are Weber, which is Tesla times square meter in the international system. So once we've defined this, we can go and present Faraday's law. So Faraday's law comes from experiments that were done in the 1830s by Michael Faraday at UK and Joseph Henry at USA and others. And these experiments showed that if the magnetic flux through a surface that was bounded by a wire, if this magnetic flux changed, in the wire there was an induced electromotive force that was equal in magnitude to the rate of change of the magnetic flux. This is what you have here written. Okay, so this here is the electromotive force, the induced electromotive force, and this is the change in time of the magnetic flux across a surface. So let's think of an example. We can take a ring, a wire in the shape of a ring, and then we take a magnet pointing with the north pole pointing towards the center of the ring, and then we just change the distance between the magnet and the ring. We can move the magnet towards the ring. If we do so, the number of field lines that cross the surface bounded by the ring, this surface here, this surface, okay, bounded by the ring, will increase. So that will change the magnetic flux across this bounded surface. It will increase the magnetic flux. So that will induce an electromotive force in the ring that's going to make it's going to induce a current, an electric current, and the sense of the current and the sense of the electromotive force is going to be that opposes the change, which is Lenz's law. Okay, so if we move to the right, I'm going to discuss this in the following slide. So here we have the same example. We have the same ring here, and we have the magnet. So if we move the magnet and we get the magnet into the ring, if we get the magnet closer to the ring, the amount of magnetic field lines that cross the surface will increase. So the ring, in the ring, they will induce a current that is going to oppose this increase of magnetic flux. And this is done by inducing a current such as that the magnetic field generated by this current opposes the change of magnetic flux. In this case, as we are approaching the North Pole and the magnetic field pointing towards the right is going to increase, then the induced current in the ring must find a way to generate a magnetic field that goes towards the left. And if you remember what we studied in the previous unit, in Unit 15, this would be a magnetic field towards the left would be caused by a current in the ring that goes the way that is shown in the picture. Okay, you have to remember our mnemotechnic rule, and you have to take the ring with the sense of the current with your 4 fingers, so that your thumb will be pointing towards the magnetic field generated. So you can see if the induced current is the one that is shown in the picture, then the magnetic field generated by this current is going to oppose the increase of magnetic flux that is coming from the approach of the magnet towards the ring. Okay, so this is the minus sign that appears here, and this is the part that we call Lenz's law, that the electromotive force is in such direction that it opposes the change that produces it. With this, we end our explanation of Unit 16, and I think a nice way to see induced currents in action is to take a look at the demonstration of the Thomson's ring, where you can find several things that we've been looking at regarding the magnetic field. You will be able to see the induction of current because the magnetic field and the magnetic field changes through the ring. Okay, so the magnetic flux changes through a ring, and then you induce a current. And you see this in this demonstration. So I'll put a link to the demonstration in the Campus Virtual. So I just suggest you to follow it and see it after this.